Good morning. Our next topic is ring counter. Okay. Before studying ring counter, we need to understand that it comes under the category called shift register counter. Okay, shift register counter. Uh, each time a question, when we find a question in this, what we call related to ring counter, um, you know, at times we may find that what are the categories of shift register counter? One type of question is what are the different categories of shift register counter, or we may a question may be asked like what is the working procedure of ring counter, or also what is the working conditions or what is working procedure of Johnson counter. Okay, we need to understand that shift register counter is a special kind of a special device, or it works both. It has the functionality of both shift register and also it works as a counter. The reasons I will explain in the following statements, and also understand that there are two basic counters, or in the case of shift register counters, one is the ring counter and the other one is Johnson counter. Okay, shift register counter. Shift register counters are obtained from serial in serial out shift registers by providing the feedback from the output of the last flip flop to the input of the first flip flop. That you will understand when we go for the design of ring counter and Johnson counter. But it follows a serial in serial out path, and also the output of the last flip flop is taken as a feedback to the first flip flop. These devices are called counters because they exhibit a specified sequence of states. That also I'll explain when we go for the design part. Also, thus a device that works both as a shift register at the same time also works as a counter device is called shift register counter, and mainly the most important ones shift register counters. First one is a ring counter. That's the heading is also ring counter. Ring counter, it's also called basic ring counter or simple ring counter. Okay, the other one is Johnson counter, a question which is frequently asked. Johnson counter, it's also called twisted ring counter, also switch tail ring counter. Switch tail ring counter. Okay, please go. Ring counter is the simplest shift register counter. Okay, and what's the, as I told, a shift register counter means there will be the flip flops are arranged as it follows a serial in serial out shift register concept. So here the flip flops are arranged as in normal shift register, that is the Q output of each stage is connected to the D input of the next stage, but the variety cases, but the Q output of the last flip flop is connected back to the D input of the first flip flop, that is it forms a ring. Okay, each case is connected like that, and the output of the last flip flop is fed to the input of the first flip flop. Okay, such that the array of flip flops is arranged in a ring, and therefore the name ring counter. Okay, please follow or understand this concept. We will go for the design part. Okay. This is how we design ring counter. Okay, this is using D flip flops. Okay, we use 4 flip flops here. Okay, the output each Q1 is fed to D2, Q2 is fed to D3, Q3 is fed to D4, and from Q4 it's taken, or the feedback is taken back to D1. This is how it works. And in the case of JK flip flops, we have two cases, right? J and K. One is a positive part and one is a negative part. So what we do is we take such a connection back, and also from Q4 bar connection is taken back to K1. Okay, please go. This is the state diagram of ring counter. Okay, it's based on the figure that we have just drawn. Okay, based on that D flip flop. You can use JK also, but based on D flip flop, we have constructed the output. So imagine there was 4 flip flops, right? FF1, FF2, FF3, and FF4. And here, what we do is, in many cases, we give the example by giving the first flip flop is set to 1. Okay, the first flip flop, that is, we have 4 flip flops, and the first flip flop is set to 1, and the rest of the values is set to 0. Okay, or only the value in FF1 has only FF1 has the value 1. Okay, and based on the clock, okay, the clock used here was based on the negative triggering. Okay, negative edge triggering. You can give positive edge triggering as well. Okay, so on each clock pulse, on the application of each clock pulse, what happens is that particular one value will be shifted right. Okay, so we had 4 flip flops. First is 1, rest is 0. Okay, after the application of the first clock pulse, what happens is 1 will be shifted to FF2 and rest of the values, or the last flip flop value will be given to first. Okay, likewise we understand that flip flop 1, flip flop 2, flip flop 3, and flip flop 4, FF1, FF2, 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 FF3, FF4. Okay, so initially this was set to initially. Okay, so no clock pulse is applied. After the first clock pulse, one value is shifted to FF2. After second clock pulse, and this will be given this value, this is shifted here, and this will be given to this part. Okay, next is after the application of second clock pulse, this 1 will be shifted here, 0 will be shifted here, and this 0 will be shifted to this position. This means 0, 0, 1, 0. After this next clock pulse, this will be shifted here, so we get 1, and this 0 will be shifted here, so 0, 0, 0, and this 1. Okay, after the fourth clock pulse means we repeat the cycle. See, 1, 0, 0, 0. So we can say that these are the cases 1, 0, 0, 0, that is based on Q1, Q2, Q3, and Q4 values. So next is 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay, and these are the things that you need to note when we learn ring counter. The number of distinct states in the ring counter, that is the mode of the ring counter, is equal to number of flip-flops used in the counter. Here we go for 4 flip-flops and the number of states will be 4 itself. Clear? An n-bit ring counter count only n bits. I think it's clear. Whereas an n-bit ripple counter that we have learned earlier, counter can count 2 raised to n bits. I think you are familiar with that concept. Okay. So the ring counter is uneconomical compared to a ripple counter, and rest is it's uneconomical, that is a disadvantage. But the advantage is that has the advantage of requiring no decoder, because it's a simple circuit. Since we read the count by simply noting which flip-flop is set, since it is entirely a synchronous operation, it's based on the clock, right? Operation, and requires no gates external to flip-flops, it has the further advantage of being very fast compared to the ripple counters. Okay, so these are the things to be noted. There is one advantage and one disadvantage and couple of advantages. This is a state diagram, this is a sequence table. Please go through. This is the timing diagram of a ring counter. Okay, how can we draw this diagram? Okay, in textbooks you may not find these values here. Okay, so the best thing you need to do is based on the sequence diagram that we have just discussed, what we do is look for clock pulse 0. There Q1 was 0 and the rest of the values was Q1 was 1, so it goes for high, and rest of the values it's low. Okay, and in the case of first clock pulse, what happened? Wait a second. One second, just hold on. Yeah, it's correct. During the first clock pulse, initially it was 100. It's correct, okay? Initially it was 1000, and in the first clock pulse, change happened is it becomes Q2 becomes 1 and all the other values are zeros. And in the case of second one, at Q3 alone is 0, sorry, high, rest of the values is 0. In the third case, what happens is only Q4 holds the highest value, rest of the values will be 0. Okay. And in the next clock pulse, that is from there repetition happens, right? 0 and 4 is almost, it's similar because it's almost like a cycle. So this becomes 1, rest of the value is 0. This is how we draw the figure, okay? Here, compare each case. In the case of fifth one, again similar to Q1. Sixth, in the case of, in the case of fifth clock pulse, 0, 1, 0, 0. Here it's similar to 1, 0, 1, 0, 0. Okay, you can take any method which is comfortable to you. You can either follow this pattern, give 3 zeros in between, or this case, or the best thing we need to do is, or the best thing we can follow is what I have just told before. Okay, that is in the case of 0, that is initially it's 1, 0, 0, 0, and what happens in the next clock pulse, this 1 is shifted right? So 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, high case. After that, again 1, 0, 0, 0, again 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. After 0, 0, 0, 1, again 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, again. Okay, likewise. This is again a high case that we have not shown. Let's go through. This is a timing sequence, timing diagram of ring count.